Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video we're going to talk about cost minimization. Before we get into the math in cost minimization, we need to introduce the concept of the isocost. To do that, we need to define a few new parameters. W is the wage. That is the price of a unit of labor, which we've been defining as L. R is the rental rate of capital. That is the price of a unit of capital, which we've been denoting with K. We will assume that these two numbers are constant, so there's no overtime pay or anything like that. An isocost is a line containing combinations of capital and labor that have the same total cost. Remember that L is the amount of labor and K is the amount of capital. So our total cost, which we will denote as C, equals WL plus RK. We are hiring L units of capital at a price of W apiece, and we are hiring K units of capital at R apiece. So our total cost will be the sum of the amount spent on labor and capital. For graphing purposes, it may be helpful to solve for K by subtracting WL from both sides and then dividing both sides by R, which is going to give us K equals C over R minus W over R times L. The interesting thing to point out here is the slope of the isocost, which is W over R. That is the ratio of the prices, the wage divided by the rental rate. Let's do an example. Let's suppose that W equals 2 and R equals 8. This means the isocost will have an equation C equals 2L plus 8K. From there we can plug in numbers for C. Let's draw a graph. Again, I'm going to put L on the horizontal axis and K on the vertical. Let's start out with C equals 160. The equation for this isocost will be 160 equals 2L plus 8K. All the combinations of L and K that satisfy this equation will cost the same amount, which is a total of 160. As usual, I'm going to find the intercepts to graph this. So if K is 0, we'll get 160 equals 2L, which means that we need to have 80. If L is 0, we'll have 8K equals 160. Divide both sides by 8, we get K equals 20. A straight line between these two intercepts will be our isocost for C equals 160. We'll do another one for C equals 200. In that case, we'll have 200 equals 2L plus 8K. The L intercept here, we would set K equal to 0. So 200 divided by 2 is 100. He's somewhere over here. For the K intercept, we need L to be 0. So 200 divided by 8 is going to be 25. Be somewhere over here. Then all we need to do is draw another straight line in between those, and that's going to be our isocost for C equals 200. And we can go from there. Isocosts are always straight downward sloping lines. As with isoquants, there are an infinite number of these corresponding to any possible C that you can think of. You can take any number, plug that in, and draw the isocost. Now that we've learned about isoquants and isocosts, we're ready to put those two together to do some cost minimization. The goal with cost minimization is to attain a certain target output while spending as little as possible on inputs. The overall idea is similar to the consumer's problem we did before, but instead of a maximization of utility, it is a minimization of cost. Thinking about this graphically, we want to get to the lowest possible isocost while staying on the isoquant that corresponds with our target output. First, we're going to go through the general process of cost minimization, and then we're going to get into our three specific production functions. The way we're going to think about cost minimization is that we want to get the best value for our money. So we're going to think about the marginal product per dollar for labor. That's going to be the MPL divided by the wage. Similarly, the marginal product per dollar of capital is going to be MPK divided by R. If the MPL over W is greater than the MPK over R, then this tells us to use more labor. because we're getting a better value for our money. Similarly, if the MPL over W is less than the MPK over R, this tells us use more capital. The only case left is if the MPL over W is equal to the MPK over R, and this tells us that we have minimized cost. We can't improve upon that allocation. So this last equation is one of our conditions for cost minimization. We can do a little bit of algebra on this by multiplying both sides by W. That's going to give us MPL equals MPK W over R. Then we're going to divide both sides by MPK to get MPL over MPK equals W over R. This condition is the marginal rate of technical substitution equals the ratio of the input prices. This should look pretty familiar because it looks very similar to the condition that we had for utility maximization. Recall as well that the MRTS is the absolute value of the slope of the isoquant, and W over R is the absolute value of the slope of the isocost. So this tells us at the point of cost minimization, those two slopes need to be the same. Our second condition is that we need to maintain our target output of Q. So we need to have F of K and L equal Q. These two equations are what come together to give us our cost minimization conditions. The point we're looking for needs to be on the isoquant, and also the slope of the isoquant needs to be equal to the slope of the isocost. This all comes together to say that we are going to find a point where the isocost is tangent to the isoquant. Very similar to the consumer's problem, where the budget line needs to be tangent to the indifference curve. To illustrate cost minimization, we are going to look at all three of our production functions. This time we're going to start with Cobb Douglas. The reason for that is that the curved shape of the Cobb Douglas isoquants are going to allow us to solve for cost minimization the normal way, like I've just outlined. The Leontief and linear production functions are exceptions in a sense because they do not have curved isoquants. They have straight isoquants. In the last video, we showed that the MRTS for Cobb Douglas is BK over AL. To minimize costs, we're going to set that equal to W over R. That's equation number one. Equation number two is that we need to be on our isoquant, corresponding with our target level of output, Q. So Q is going to be equal to K to the A, L to the B. We now have a system of equations with two unknowns, that's K and L, and two equations with which to solve. To illustrate this, we are going to go back to our example Cobb Douglas function, which was f of KL equals K to the 1/2, L to the 1/2. We need to set up our two equations. For equation number one, we have 1/2 K over 1/2 L equals W over R. Those 1/2s cancel, so we just get K over L equals W over R. Remember that the 1/2s canceling here is just because the exponents were the same. That does not have to be the case. For our second equation, we have Q equals K to the 1/2, L to the 1/2. To do our cost minimization, we're going to use W equals 2 and R equals 8, and we're going to have a target output of 10 units. Let's plug all these numbers in. So we're going to get K over L equals 2 over 8, and we're going to have 10 equals K to the 1/2, L to the 1/2. We now need to use substitution to solve this. As always, there's many ways that you can go about this. I'm going to start with this equation right here and solve it for K. First of all, notice that 2 over 8 is 1/4, and then I'll multiply both sides by L to get K equals L over 4. I'm now going to plug this into our second equation. So where we have a K, I'm going to plug in L over 4. So that's going to give me 10 equals L over 4, since there was a K there. And all of that will be to the 1/2, L to the 1/2. Remembering our rules for exponents, we need to distribute the 1/2 power onto the L and the 4. So we're going to get 10 equals L to the 1/2 over 4 to the 1/2, which is just 2, times L to the 1/2. When we have two terms multiplied with the same base, we add the exponents. So we have L to the 1/2 plus L to the 1/2, which is just L to the 1. So we have 10 equals L over 2. Multiply both sides by 2, and we're going to get L equals 20. This means our cost minimizing combination will have 20 units of labor. To figure out how much capital we need, we'll just plug it in right here to get K equals 20 over 4, which is 5. To find out how much this costs, we'll plug that into our cost equation. C equals WL plus RK. So what we're going to get is W is 2, L is 20, R was 8, and K was 5. This is going to be 40 plus 40 equals 80. The last thing that I'm going to do with this is to draw the graph. We've got L down here, K up here. First thing I'm going to do is draw our minimized ISO cost. Since we just figured out that the cost is 80, we need to draw the ISO cost that corresponds with 80. So we have 80 equals WL plus RK, which is 2L plus 8K. To figure out the intercepts, remember to plug in 0 for K, so it's going to be 2L equals 80, so then we are going to need 40. And for the K-intercept, plug in 0 for L, so we get 80 equals 8K, so we're going to need 10. I'll use a red line to do our ISO cost. Next, I'm going to graph out our cost minimizing point, which we found was 20 and 5. So this point is about here. Next, we're going to draw our ISO quant corresponding with a quantity of 10. So that's going to be 10 equals K to the 1/2, L to the 1/2. It doesn't have to be perfect, but we do know that it has to be tangent at that point that we just found. So this is going to be our Q equals 10 isoquant. We can also use this picture to graphically think about how the cost minimization works. This blue curve, the isoquant, we know that we need to be on that curve somewhere to be able to produce 10 units, but we're trying to find the point along that curve that has the lowest possible cost. We could draw in some other isocosts that also cross over that isoquant. This point and this point also produce 10, but we know those are more costly than the one we found. In fact, we know that all of the points in between those two on the blue curve in this area down here are cheaper. And so one of those is better. And we're going to keep pushing the isocosts in towards the origin until we reach that point of tangency. If we keep going, these points are even cheaper than the ones on the red line. So that would be great, but unfortunately, those points do not produce enough output. Those points all lie on lower isoquants than our Q equals 10 one. So those are not going to work either. And so we're going to end up with this cost minimizing point, 5 and 20 in our case, where the isoquant is tangent to the isocost. Hopefully you are seeing the parallels between this and utility maximization that we've done before. Next, we are going to look at the linear production function. With the linear production function, we have f of KL equals AK plus BL. To calculate the marginal product of labor per dollar, we take the MPL, which is just B, divided by W. MPK over R is going to be A over R. With Cobb Douglas, we set these two things equal to each other and figured out the K and L that would make that work. The problem with doing that here is that K and L don't appear anywhere in either of these expressions. B over W is just a constant. A over R is also a constant. These things might happen to be equal to each other, or they might not. There are three different cases that could happen. We could have B over W greater than A over R. Remember that this means use more labor, since it's a better deal. Since these are constants, labor is always going to be the better deal, so this means To produce Q units of output, we need to have labor equal to Q over B. We're going to use all labor, and we're going to have K equals 0. Remember that each unit of labor produces B units of output, so if we're going to produce Q, we need Q over B. In the second case, we have B over W is less than A over R. In this case, capital is the better deal, so we're going to use no labor, and we're going to set capital equal to Q over A. This tells us there is no reason to ever use a mix of labor and capital. It's always better to use either all labor or all capital, and which one depends on the production function and the prices. It is also possible to have B over W equal to A over R. In this case, you can't go wrong. It doesn't matter how much labor and capital you use as long as total production adds up to Q, because capital and labor both provide the same value for money here. Let's take a look at how this works with our example production function, f of k, L equals 3k plus 2L. Suppose that our wage is 4 and rental rate is 8, and our target output is 60. First thing to do is figure out MPL over W. MPL is 2 and W is 4, so we get 1/2. Then we're going to do the MPK over R, which is 3/8. Think about this for a second, and we can see that 1/2 is greater than 3/8, which means that labor is the better value for money. This means we're going to use all labor. So we have 60 equals 3 times K, which is 0, plus 2L. Get rid of that. Divide both sides by 2, and that's going to give us L equals 30. We, of course, know that K is 0. To calculate the total cost, we have C equals WL plus RK, and we're going to just plug in the numbers. So what we have is 4 times 30 plus 8 times 0. That comes out to 120. Let's draw the graph of this one. Again, we're going to put L down here and K up here. First, we'll graph the ISO cost, which is 120. That's our total cost that we just calculated. So we're going to try to find all the other combinations of inputs that also cost 120. So that's going to be 4L plus 8K. Thinking about the intercepts as usual, 120 divided by 4 is 30, and 120 divided by 8 is 15. So that's going to be our ISO cost. For our ISO quant, we have our target output of 60 equals total production of 3K plus 2L. The L-intercept here is also going to be 30, but our K-intercept will be 60 divided by 3, which is 20. Put that about here. Connect those up. What we end up with is an ISO quant for Q equals 60 and an ISO cost for C equals 120 that are both straight lines. Remember that the MRTS is the absolute value of the slope of the ISO quant. In this case, it's 2/3. And the price ratio is the absolute value of the slope of the ISO cost, which in this case is 4/8, which is 1/2. And we can see on the graph that the ISO cost is a flatter line than the ISO quant, which is the steeper of the two lines. As with Cobb Douglas, we can draw in some other ISO costs to see how this worked. I'm going to draw in another ISO cost here. This point is on the ISO cost and the ISO quant, but we can do better by moving down this direction, down to one of these points. Just with Cobb Douglas, we're going to keep pushing our ISO cost inward until we hit the last possible point that's still on the ISO quant, which in this case is down here at 30 labor and 0 capital. Again, we could try to keep going, but this ISO cost, although it would be better, is no longer touching the ISO quant, meaning it's not producing enough output. Had our ISO costs been steeper than the ISO quant, we would have ended up with a solution with all capital and no labor. But since it was flatter, the last point we end up with has all labor, no capital. Our third and final production function we're going to deal with is the Leontief. Remember that our Leontief production functions look like this: the minimum of AKBL. Cost minimization with Leontief is relatively simple compared to the other two. All it requires is that AK equal BL equals Q. This ensures that we don't waste any inputs. We'll use exactly enough capital and exactly enough L to produce exactly Q. In our last video, we showed that the isoquants for the Leontief production function are L shapes, and this basically says that the cost minimizing point is the corner of the L. Let's do our example, which was f of KL equals the minimum of K and 1/2 L. Suppose we have a wage of 4, rental rate of 2, and a target output of 20. We'll just plug all of those things into these equations right here. So first of all, we need AK equal to Q. Here A is 1, so we just have K equals Q, which is 20. For the second one, we have 1/2 L equals 20, so that means L is going to be 40. That's really all there is to it. We can then plug these in to figure out the total cost. Remember, that is WL plus RK, so we're just going to plug in the numbers. What we have is 4 times 40 plus 2 times 20. That's going to give us 160 plus 40, which is 200. Now that we have all this information, we can graph this one. First thing I'm going to do is identify our cost minimizing point, which was 40 and 20. It's going to be right about here. Next, I'm going to draw our isoquant, which is going to be an L shape with our cost minimizing point being the corner. This is our isoquant for Q equals 20. Our isocost is going to correspond with the total cost of 200 that we just found. So 200 equals WL, W is 4 this time, plus RK, R is 2 this time. As always, I'm going to use the intercepts to graph this thing. For the L intercept, set K equal to 0, so we're going to get 200 over 4 is 50. Be about here. For our K intercept, we have L equals 0, so 200 divided by 2 is 100. That's about here. I'm going to draw a line between these two. Now this needs to go through our cost minimizing point, and it looks like I did a pretty good job with that. As before, we can look at some other possible ISO costs. This point and this point also produce 20, but there's no reason to do that because we can do better by moving in. If we keep pushing our ISO costs inward and inward, the last point where they're going to touch the isoquant is that corner. If we were to keep going, then we are now off the isoquant. We don't want to do that. We've now shown how to minimize costs with our 3 production functions. In the next video, we're going to talk a little bit more about cost.